Hi, everyone. I'm Harlan Haskins. I'm a compiler engineer and a Swift compiler contributor. You've all been in here listening to some really great and in-depth technical topics. So I'd like to just sort of lighten things up a little bit and give you a deep dive into the Swift compiler internals. All right. No, I'm really actually thrilled to take the opportunity to introduce you all to the Swift project, and I hope that we can get some good enthusiasm for contributing to Swift out of this. So, I'd like to begin this talk with a brief overview of all the Swift-related Apple projects on GitHub. Next, we're going to talk about how to set up your environment for building Swift. Then we'll move on to getting started with a contribution. We'll go over a couple of tips and tricks to help you get the most out of your debugging experience. And then finally, my colleague Robert Widmann will go over the process of solving a compiler crashing bug live on stage and submitting it to GitHub. So let's get started. So, Swift is more than just a compiler. It also includes the core libraries like Foundation, Xctest, the test running system, libdispatch, the concurrency primitives, tooling like the Swift package manager, and more recently some open source projects like the Swift implementation of Google's protocol buffer library, and also the new non-blocking I/O library, Swift NIO. The Swift project also includes forks of LLVM, Clang, and LLDB, all separate compiler tools under the LLVM umbrella that Swift has made modifications to allow it to work. So we're going to focus in this talk mostly on just the Swift compiler project. But the Swift compiler project is also composed of many different sub-projects, each of which have dozens of or hundreds of open opportunities for contributions. So let's talk about how to get started contributing to Swift. The first thing to do is you're going to want to start with a goal. Find an issue that you want to fix. Find something that has directly impacted you, like a compiler crash that you've experienced while editing your own code. This can take on many things. These can be typos in the documentation and the rewording that you need to do to make them better. These can be unclear error messages or missing errors the compiler doesn't emit. These can be new features for the language and the standard library. Additionally, we have an entire class of bugs on bugs.swift.org that we call starter bugs. These are identified by the core contributors to the language as bugs that are really good for just getting a bite-sized introduction into the compiler and allowing someone to sort of get their feet wet with the system. And then also there's the more serious bugs and crashes in the compiler that you're going to see more of later in this talk. There's a lot of opportunity in the Swift compiler for fixing things. So as with most open source projects on GitHub, the first thing you're going to want to do is fork it. Create a fork for you to stage your own changes, and then you're going to pull request them back into the Swift repository on GitHub. Then once you have your fork, you're going to clone it to your local machine to do your work. Before we go any further, we need to talk system requirements. You've got to have at least a modern Mac or a modern PC with at least 8 gigabytes of RAM, and at least 25 gigabytes of disk space. But we recommend at least double that. Oh wait, no, this should be a Linux box. That's better. So next, you'll need to install the dependencies. Swift uses a build system called CMake. It's a very popular build system for C and C++ projects that aims to modernize and add more features on top of, say, make or autoconf for some of the other existing build systems. And it also uses a build driver tool called Ninja. This is essentially what CMake will invoke to actually call the compiler and actually build the project. You can install both of these with Homebrew on macOS or whatever your favorite package manager is. On Linux, please copy the install command from the README. Please don't try to type it in from this slide. All right. The Swift project ships with a bunch of utilities to make development easier and more convenient for you. We've highlighted a couple of tools here that we feel are important, but there are many, many more tools just waiting to be discovered in that utilities directory. So the first one we're going to talk about is called update checkout. This is going to be the first script that you run after you've cloned Swift. Update checkout fetches those non-compiler parts of the Swift project, Clang, Xctest, Foundation, Dispatch, and it puts them all in the right place for the build system to know how to build them. It's smart enough to be run from any directory, so if you just run that utility, it will set you up with a buildable installation. So we pass -- clone here because we haven't yet cloned the projects. So this is just the first time you run update checkout, you want to tell it to clone them initially. When you run update checkout subsequent times, it's going to fetch and update the existing checkouts. So if you intend to work on any of the other projects, like say you want to make a change to the package manager or Clang, then you should clone those first before you run update checkout. Then it won't re-clone the Apple ones over your existing checkouts. The next tool is the bread and butter of Swift developers, and it's called BuildScript. BuildScript is a high-level abstraction over the underlying CMake build system. It is a sorely needed abstraction. If anyone in this room has dealt with CMake, you know exactly what I'm talking about. It vastly simplifies the user experience of CMake, which, yes, we really need. BuildScript is highly configurable. There are flags for the configuration that you want to build with. There's flags for actions that you want to do before and after. If you run if you run BuildScript with the help command, you'll get more information about the flags that are available. But these are one example of flags that you're going to want. But because it is an important part of your workflow as a contributor, it's important to know some common flags. The most common configurations involve 3 choices. Do you want to build with Xcode or build with Ninja? Do you want to build in debug mode or release mode? And do you want to turn on assertions or turn off assertions? So with Xcode, you're given an Xcode project from which you can build, edit, and debug the Swift compiler. You can select this by providing the Xcode or X flag to BuildScript. And importantly, CMake does not know how to tell Xcode to run these tests. You still have to use the command line if you're going to do that. This is really important. With the Ninja configuration, you can just run the tests from BuildScript, but there's no IDE integration, which may be a deal breaker for a lot of people in this room, myself included. The Ninja configuration is the default configuration, so you don't need to pass a flag to choose Ninja. Now, for debug and release. These are similar to the differences between a debug and release build in Xcode or in Android Studio. The debug configuration will build an unoptimized copy of the compiler with full debugging information. And it takes a lot longer to compile than a release build, but the debugging experience is a lot better. So you can build this configuration by passing --debug or -d to BuildScript. And then the release configuration is the opposite. It builds optimized, but with reduced debugging information. And it's not recommended that you actually do your development with this flag on because it does make it a lot harder to debug. But it might help when you're running the test suite. You can build this configuration by passing --release or --R. And then this last one, we really debated on whether to include even telling you that you can turn assertions off. But in the interest of completeness, we want to let you know that you can turn assertions off, but we recommend that you don't. And in fact, we're not going to tell you the flags. You can go find those on your own. The reason we say that, though, is because the build folder is the concatenation of these 3 options: Xcode, debug, assert, Ninja, release, assert. And these are the 2 most common BuildScript invocations that you're probably going to need if you want to build an Xcode project or if you want to build a Ninja project. I'll let folks take pictures of the screen if they want. All right, so this final utility we're going to talk about is lit. Lit is LLVM's integrated test runner. It's actually not a Swift utility. It's found in LLVM's utilities directory. It has a lot of powerful features, but it's mostly optimized for integration testing. That is, testing the entirety of the compiler. You give it a file, you check the output. Here, we provide a sample lit invocation. You should replace config there with your specific configuration folder, Xcode debug assert or Ninja release assert. And then we also point lit at the test directory, but in the build path. This is the path that mirrors the test directory in the source path. This is really important because lit creates this sort of shadow copy of the test directory structure. And it's a little weird. Most of the time, you're just going to want to run all the tests this way. Now, we give it 2 flags, succinct and verbose. Succinct means that when the tests pass, the output is short. And verbose means when a test fails, the output is long. This is usually what you want with tests, because sometimes passes can get noisy. So now, before moving on to tips and tricks, I want to briefly show you how to set up Xcode for Swift compiler debugging. When you open the generated Xcode project for the first time, you'll be presented with the option to manually or automatically create schemes. While it is tempting to select the automatic option, CMake populates this project with 722 schemes. Now, this can slow down the IDE a lot, and not to mention slowing down you, because every time you want to switch building the compiler or building the standard library, you're going to have to wade through about 700 possibilities to find the exact one. You'll see Robert try to do it later on in the talk. In contrast, manually specifying schemes lets you pick the 3 most important targets. All build does what it says. It builds everything. This is a standard CMake target, which is just the top level target that just builds everything. You'll want to run this one time to get everything built, and then never again. Because subsequent builds, you'll want to build either Swift, the compiler itself, or the standard library. Now these are 2 separate projects. A lot of you who write Swift might not have internalized the difference between the compiler and the standard library, but the compiler is written in C++ and the standard library is written in Swift. They're 2 separate pieces, and so they have separate targets. As you gain more experience with the project, you may find it necessary to add more targets. There are testing tools that you might need to add targets for. To do this, select New Scheme in the Scheme list in the main toolbar in Xcode. We'll demonstrate this later in the talk. So now I want to talk to you about some tips and tricks that might help you establish your own workflow. Always compiling your code every time can be expensive, time-consuming, and frequently is unnecessary. The compiler has built-in ways to stop the compilation process early. If you have a bug that's in the parser, you probably don't need to let it survive through to generating a binary. You want to just stop it before parsing. To do that, you can pass one of these flags. There are several more, but these are the most common ones that you're going to use. We list some common phases, but we'll give you a high-level overview of what these phases do later on in the talk. So, another tip, if you're running on Mac OS and you want to import Foundation or use any other Objective-C-based library, you'll need to tell Swift where to find the SDK and enable Objective-C interoperability. It's a lot of words, I know. Copy these flags. The easiest way to find where your SDK is to just ask xcrun to show it, and then you can just pass it in the bash command. So, I want to give you a couple of tips for effectively testing and debugging. So this next test is a flag that you can pass to lit. Now lit will by default run all the tests in the test directory. Swift has 17,000 of them, more or less. And so it might be useful to say, no, I want to run this specific test. So you pass the -- filter flag. This is a regular expression that will match whatever tests you want to run and will skip the tests that don't match. This is super useful. This is probably one of the most useful slides in this entire talk, is running just 1 or 2 of the tests. So next, when you're debugging crashes, Swift has this incredibly useful facility called pretty stack trace. Now, a lot of times when you hit a fatal error or throw an exception in your program, you get a stack dump that shows you exactly all the functions that are called, but that's not particularly readable. And if you build up a lot of abstractions, then there's a lot of intermediary frames that just sort of pollute it and add a bunch of noise, and it's hard to figure out what's actually going wrong. Swift, on the other hand, will tell you in these pretty stack trace entries, in English, what the compiler was doing when the crash occurred. It's laid out in pieces. So it'll start by telling you where the crash happened, and then it'll say what it was working on at the time, and finally, where in the code you can find what it was working on. There are also a few terms you're going to want to know when submitting patches on GitHub. Now, gardening. Gardening refers to any contribution that makes changes to non-executable code, including comments, documentation, README files, manifestos, if any of you are familiar with the Swift process, specifications of behavior, and so on. If you find typos or any sort of incorrect information in that, it's really useful to get those to get contributions fixing that grammar and that non-executable code. They're very important to projects of this size and scale. Now, QOI is a rather odd phrase. I don't think anyone actually knows what it really means, but we've come to understand it means quality of implementation. This seems to have arisen in the middle of LLVM's development. Someone decided to use this term, and I guess it just stuck. but you'll see people using it a lot. And it basically means changes that aim to improve the structure of the code, but without changing behavior. So some examples like selecting a better data structure for something, or refactoring an interface to a class, or cleaning up duplicated code all around the compiler, or adding an assertion for something that should be checked. QOI changes should go through a review by the person that wrote the component that's being fixed. Now, to put all these concepts I've put in front of you, and it's been a lot, I understand, to put all these into practice, I want to invite my colleague Robert Widmann to talk about compiler crashes, what makes them particularly interesting, and how to fix them. Thank you so much.
Just a moment. Hello, everyone. My name is Robert Widmann, and I'm a compiler engineer and a contributor to Swift, just like Harlan. So I'm sure you've all seen this before. This is the error message Xcode displays when the compiler crashes. This is immensely frustrating for Swift developers everywhere, and it's immensely frustrating for me as a Swift programmer. The crash is an indication of an assumption that has been broken during some part of the compilation process. The Swift project prefers this failure mode. Loud crashes are easier to debug and much better than miscompiling your code silently. Though compiler crashers for us as compiler engineers are compelling, and for you as potential contributors, they present an excellent opportunity to learn about the compiler in depth. Because they usually involve the interaction of many moving parts, compiler crashers are a natural way to get hands-on experience with many components at once. The compiler can be roughly split, for example, into the front end and the back end. The front end here is responsible for reading files, breaking them apart into meaningful pieces, reassembling those pieces into a syntax-preserving data structure in the parser, and later annotating those with types and checking correctness in semantic analysis. The back end is composed similarly. Your code is transformed into the Swift Intermediate Language, or SIL. From there, it is optimized, analyzed, and transformed again into another language called LVM Intermediate Representation, or IR for short. This IR is later lowered to machine code through a forest of analyses and optimization passes, and eventually, a binary result. So, before we move on, let's recap. You've learned how to clone and build the Swift project. You've learned a few tips and tricks that we have encountered so that you can start building your own workflows around working with the compiler. And now, we want to put all of this knowledge to work. And to do that, I'd love to give you a demo. Let's fix a bug. So that doesn't work. Beautiful. OK. So, before we get started, I need to be candid. The Swift compiler is written in C++. C++ is a sticking point, I know. For a lot of people, it can be a deal breaker. But LVM C++ is a little different than maybe some of the C++ you may have encountered, however you have. It's a very high-level dialect of C++. And we want to make this as accessible as possible, and we realize the only way to do that is to unsilo a lot of the information that we've learned along the way. If, for any reason, you have any reservations about using C++, or perhaps you need an introduction to LVM-style C++, please send an email to the Swift forums or contact one of us personally, especially while we're here. We'd love to help you. So, let's get started. We're going to be taking a look at a crasher that actually exists today. So we keep the compiler crashers in a directory called compiler crashers. That makes sense, right? So, oops, that's not how words work. So, under the validation tests directory, you can see we have the directory compiler crashers and compiler crashers 2. The difference between these two is fairly negligible. But generally, the convention is compiler crashers is reserved for fuzzing-guided crashes. Compiler crashers 2 is reserved for human-created crashes. We also have the corresponding compiler crashers fixed and compiler crashers to fixed, which, if you can guess from the name, is where our fixed code is going to ultimately wind up. So let's take a look at the crash. Does that look like Swift to anybody? This code currently crashes the Swift compiler. And you notice that it's unstructured, it's unruly, and it's pretty freaking close to not being valid Swift. I just want to give you a feel for how machine-generated crashes look. We're going to come back to this. First, we're going to follow Harlan's advice and switch to Xcode. So you'll notice here I have no schemes. I'm going to manually create them. By going here, selecting New Scheme. All build comes up first, conveniently. Going here again, selecting New Scheme. Swift stdlib isn't too far behind. And selecting New Scheme. Swift is in the middle of this list. We weren't kidding about 700 targets. OK, everything's all set up. And we need now to pass the flags to make the compiler crash. We could do this manually. We could go back to the test. We could figure all this stuff out. Let's use lit. So we're going to switch. And we're going to run lit. LVM is the current directory. My shell is going to complete this. You do not have to memorize this invocation. It's going to be rather long. So you can see, quite quick. Runs the thing, got a bunch of diagnostics, got a failing test. Ooh, look at all this garbage. OK, well, this is what appears in the bottom of that lit invocation. And just like Harlan was saying, we have this nice, pretty stack trace. You notice that it's numbered, tells you what it's doing while type checking, while type checking, while type checking, while validating. We have this original stack trace. And then we have the program arguments. We need those. We're going to steal them. OK, now we'll return to Xcode, enter the scheme editor, and paste them. That's it. OK, let's run Swift. That's quicker than I expected. All right. Oh, DiLD, when will you be fast? OK. Crash. Look at that. All right. We hit an assertion in a component that we call the iterative type checker, or the ITC for short. And we notice immediately the assertion is related to a request. The ITC is a request-based semantic phase of the semantic analysis. It's meant to be a piecemeal way for the compiler to grab types. Requests are just the way that the compiler tells you it needs something. So a natural instinct is to print. So we're going to print the request. And several lines of garbage later, this is the only important part that we need. The kind of the request is an unqualified lookup in a declaration context. Now, that's jargon. If you had no idea what that meant, lookup is what happens when the compiler needs to match a name to a declaration. Here, we have an unqualified lookup because there's no dots in the name that we're looking for. OK, so let's look 20 frames down at line 24 in the stack page here. And you notice it's actually called, if you'll excuse me, unqualified lookup. So we're going to look up in module a particular name with some grab the results, doing an unqualified lookup, a bunch of other arguments that don't mean anything to us. And so we're going to print the name that we're looking for. Oh, what the? Oh, that's not a name. Oh, no. Well, it turns out C++ it doesn't necessarily give you the best representation of things in the debugger. We need a different way to get at this information. So we're going to try again with a dump. Isn't that much better? So pretty much everything in the compiler that you need has one of these dump methods. If you find that it's particularly difficult to read the output, call dump. You'll get much, much easier output to read. Here we see that it's trying to look up the less than operator, or maybe it's clear to me. Let's return the crasher and see where that is. So, if I can find my cursor. Less than appears in two places in this file. One on line 13, one on line 17. This is ridiculous, though. Like, how am I expected to read this? How am I expecting you to understand this? Let's clean this up. So I'm going to skip the process that I used to clean up, but it's roughly, let's rename some variables, let's indent the code, let's, make it not as garbage. And it turns out, you get this. Isn't this so much better? So this is much more clear that this is not valid Swift. And you can even see the parser, Xcode has figured out exactly what's wrong here. We have an extension nested inside of a class, inside of another class, and there's a protocol inside of that, which should never happen. Extensions and protocols not allowed to appear inside of nested contexts. These are our next clues in this race. So the last piece of the puzzle is, how is lookup finding its way into this invalid context? I mean, surely you would expect it wouldn't even look at all. Well, here's the trick. You notice this conveniently named member called bomb. You notice it uses less than as a prefix operator. If you're the Swift compiler and you see less than, your next job is to look up less than and match it to a declaration. And in order to do that, you have to walk into an invalid context. So this is our hypothesis for how this bug is being caused. We're going to load all the members of the type. We're probably going to drill through them. We're going to find this invalid thing. And because lookup always sort of assumes that it's in this valid state, I mean, why wouldn't it? It's going to grab garbage, and it's going to put garbage into compiler, and compiler will crash. So let's go back to Xcode and put all of this together. So first, we're going to rerun this. And we'll do some sanity checking here. We'll go back 24 frames. We're still crashing in the same place. And we'll go 20 more frames up and print the declaration that it's crashing on. It's a pointer this time. Bomb. Perfect. OK, how do we fix this? So our suspects from the stack trace that we have are either the type checker, way down here, or name lookup, way down here. And the natural instinct is the crash occurred in the type checker, therefore we have to fix the type checker. But that's not correct. The type checker isn't wrong. The type checker is using invalid information submitted to it by lookup. So lookup is the only place that this possibly could have gone wrong. So we have to think, what in lookup could be causing this? Well, if any of you remember Dave DeLong's talk earlier, you'll know that one of the more difficult problems in computer science is cache invalidation. It turns out that's the answer here. So there's a thing called the source lookup cache. And the source lookup cache can get populated by invalid declarations. And it turns out that it likes finding those invalid declarations in the process. It causes lookup to find those invalid declarations, and it causes our crash. So let's put in a really easy fix. If the declaration is invalid, skip it. We'll add some comments. Excuse my typing. And build and run. Aha. And no more crash. Okay. We're not done yet. One more thing. We have to put this on GitHub, right? So I am going to very quickly switch over to a branch containing my changes. Oops, let me stash this and check out our wonderful branch. Oh, it looks like I've already pushed the changes. OK, so let's go to Safari. So all you got to do, submit us a nice pull request, contains your changes, and invoke CI. And that's it. All right. So, in conclusion, we hope that you got quite a lot out of this presentation. We realize this was an enormous amount of information and that you'll come away with this with a lot of questions. And we want to thank you very much for listening to our presentation on becoming an effective contributor to the Swift compiler. We're very excited to see more people from this wonderful community get started and get creating. So we admonish you, go forth, break things, and fix bugs. In general, we can be found on Twitter and on the Swift forums. Thank you for your time and attention, and we'll take questions.